Welcome everybody to our next video in our series of power expansions of functions. Here we'll look at power series expansions of some common functions. So let's begin by recalling our definition for Taylor series expansions. So if we assume that f is going to be a function that has derivatives of all orders at a particular point, then we define the Taylor series expansion for f as being the sum from n equals 0 up to infinity, the nth derivative evaluated at a divided by n factorial, those are going to be our coefficients, and then times x minus a to the n, so that our power series is then centered at a. In the particular case that the expansion is done around 0, that tells us that we're really using a Maclaurin series expansion for f. So with this in mind, with this definition, let's start looking at some of our common functions, or ones that we run across pretty regularly, and see what the power series expansions for those functions might look like. So let's start off with our function f of x is equal to e to the x. Now, this one is pretty straightforward because we know that the nth derivative of f is always just going to be, again, e to the x. That was the awesome part about e to the x. All of the derivatives were just e to the x. And so if we want to do a Maclaurin series expansion, so we want to expand around 0, for each one of those. So we look at the nth derivative of f, and we want to evaluate that at x equal to 0. Well, it's just going to be e to the 0, so they're all going to be 1. And so just a straightforward application of the definition of the Taylor series expansion, we get our expansion for e to the x as just being the sum from n equals 0 up to infinity of 1 over n factorial x to the n. So now we can ask ourselves, well, where is this series actually going to be valid? And for that, for our interval of convergence, we'd need to go over to the ratio test. So for our series expansion of e to the x being 1 over n factorial x to the n, well, if we apply our ratio test, so we look at the limit as n goes off to infinity of the absolute value of a sub n plus 1 over a sub n. So what will this be? Well, you have the limit as n goes off to infinity, our n plus first term, which just looks like x to the n plus 1 over n plus 1 factorial, divided by x to the n divided by n factorial. So now kind of cleaning that algebra up just a little bit, we have the limit as n goes off to infinity of x to the n plus 1 over our n plus 1 factorial times n factorial over x to the n. Well, canceling now, what will cancel, our x to the n's cancel out. And then for our factorials, we have the limit as n goes off to infinity. We can rewrite that n plus 1 factorial as n factorial times n plus 1. So we have our x on top, and then we have an n factorial. So the n factorials cancel out. And so what we're left with then is just the limit as n goes off to infinity of the absolute value of x over n plus 1. Well, as n goes off to infinity, x is going to be fixed. That automatically gives us a value of 0. And so what this tells us is that we have an infinite radius of convergence. And so our power series expansion for e to the x is actually going to be valid from minus infinity out to infinity. So this gives us one of the power series expansions for one of our most common functions.